Okay, can you hear my voice?
Yes, it's clear. You can begin.
Assalamualaikum warahmatullahi wabarakatuh and good morning to all distinguished speakers, respectful audience and organizing committee. Thank you very much for giving me this opportunity to present in your prestigious conference. I am Noraini Ahmad from University of Malaya. We present to you our research entitled Biomimetic amphiphilic glycolipids nanoparticles as new drug carrier systems. So what is glycolipids? Okay, glycolipids is you can obtain from renewable resources such as sugarcane, tapioca, and so on. So this type of glycolipid is characterized as a non-ionic surfactant which dissociate in the solution to form self-aggregate structure through hydrogen bonding. So this glycolipid also can have very rich phase behavior. So it can form different liquid crystalline phase behavior such as magnetic A, hexagonal phase, cubic phase, and so on. And then this glycolipid also can self-assemble in the solution to form different aggregates such as hexosome, liposome, ribosome, and so on. Not only that, glycolipid also biocompatible to our blood and also easily biodegradable. So with these properties, glycolipids can have very wide practical applications in cosmetics, pharmaceutics, and also cosmeceutical applications. Why this happen? Okay, this is due to the structure of glycolipids, in which glycolipid consists of hydrophilic head group and hydrophobic tail. As we know that hydrophilic means that the head is water-liking, whereas the hydrophobic means that the tail is water-hating. So with these properties, this surfactant can self-assemble in the solution to form different aggregates. So now let's look at the liquid crystal types. So firstly, thermotropic liquid crystal. Okay, liquid crystal phase form on heating or cooling as temperature is changed. So this type of state, okay, is the state between solid and liquid. As you increase the temperature, the solid phase melting and form liquid crystalline phase. And then when you further heat the sample, okay, until the clearing point, okay, you can form liquid phase. Whereas lyotropic liquid crystal exhibit phase transition as function of both temperature and concentration of the liquid crystal molecule in solvent, typically water. So as you can see from this figure, from the left to the right side, increasing the water content, you can see the formation of inverse micelle, okay, and then until the normal micelle formation. So now let's look at the self-aggregate structure in solution. Firstly, let's look at hexosome. Hexosome is an inverted hexagonal liquid crystalline structure or dispersion. So this one, commonly we can observe under cryo-TEM or TM as hexagonal or close to spherical shaped structure. And then vesicles are aggregates of surfactant molecules in a solution that self-assemble to produce safe-closed bilayer-like structure. So commonly, we can observe under microscope as spherical shape. And then finally, what I will present to you today is about nanoemulsion. Nanoemulsion consists of two immiscible liquid, oil in water or water in oil emulsion, with one liquid being dispersed as very small spherical droplets in nanometer range in the other liquid, which is stabilized by a surfactant. So this commonly, the droplet's diameter is less than 200 nanometer, and then it optically transparent or translucent bluish. Okay, now let's look at the objectives of the research. Firstly, to characterize the physicochemical and liquid crystalline properties of the branched-chain glycolipid. So here I will explain to you in detail about 2-hexadecyl glucoside and 2-hexadecyl maltoside. Secondly, to investigate and characterize the structural properties of glycolipid self-assemblies. So here I also will explain to you on the 2-hexadecyl glucoside hexosome and 2-hexadecyl maltoside vesicles formulation and characterization. Thirdly, to formulate nanoemulsion with the incorporation of branching glycolipids into ternary model of water, chromophore, and medium chain triglyceride system. So this system actually formally have been investigated by a group of Conchita Solans and investigate the stability of the system. And then finally, to evaluate the efficiency of encapsulation and release of drug from the nanoemulsion system through the in vitro study. Okay, now let's look at the first part, physicochemical characterization of branching glycolipids. So these are the methods that have been conducted. Firstly, determine the presence of liquid crystalline phases by detecting the enthalpy changes associated with the phase transition by using differential scanning calorimetry. Secondly, is thermotropic study of liquid crystalline texture. So this texture have been observed under optical polarizing microscope. And then we also investigated lyotropic properties of the liquid crystalline texture by using this optical polarizing microscope. Finally, we confirmed the presence of liquid crystalline phases by using small angle X-ray scattering techniques. So these are the structures of two molecules that have been investigated. Firstly is 2-hexadecyl glucoside with beta dominant. So here you can see the second one is 2-hexadecyl beta D maltoside. So the difference here is the head group. As you can see that here is the glucose group and then this one is a maltose group, which means that the second structure is more polar compared to the first one. And then they have identical branching, which are C16. Okay, this is the result of differential scanning calorimetry, which shows to you the result for 2-hexadecyl glucoside and maltoside. As you can see that for the first one, for 2-hexadecyl glucoside, the first heating cycle and the second heating cycle is more or less the same, close to one another. So reproducible the peaks means that the sample is stable against thermal degradation. Same goes to 2-hexadecyl maltoside. The first one, we obtain the heating, the clearing temperature 179, whereas the second one is 176 degrees Celsius. So this also shows to you the sample is stable against thermal degradation. So this also depicts that the sample have certain liquid crystalline phases. So this proved by the optical polarizing microscope study under thermotropic study. So for the first figure here, shows to you a focal conic texture of columnar phase of 2-hexadecyl glucoside. Upon heating, you can see certain structure, but when you cool down, you can get a clearer texture of focal conic texture of columnar phase for 2-hexadecyl glucoside. So this surfactant is more hydrophobic compared to maltoside. When you can, as you can see here, this 2-hexadecyl maltoside shows to you a typical fan-shaped texture of smectic A phase. So now let's look at the lyotropic study by this optical polarizing microscope. So for 2-hexadecyl glucoside, okay, when you introduce water, okay, by contact penetration technique, the water penetrates to the sample from isotropic solution, then form inverted hexagonal phase. Whereas here, when you introduce the water, you can see from isotropic, okay, to the lamella phase, and then goes deeper, you can see the smectic A phase. So this is the clear observation of multi-cross structure under the optical polarizing microscope, shows to you the formation of vesicles. Okay, this is the result from small angle X-ray scattering techniques for 2-hexadecyl glucoside to confirm the formation of inverted hexagonal phase. So as you can see, for dried sample, means that without solution, Okay, the D spacing is 2.5, whereas the lattice spacing is 3. For the hydrated sample, when you introduce the sample with water, in excess water, then you measure the SUX. So you can see the D spacing increases to 3.8, whereas the lattice spacing to 4.4. So why this occur? So this shows to you that there is interaction between the sugar head group with water molecule, okay, through the hydrogen bonding. So that's why the molecules swell further in the solution. So this one is the small angle X-ray scattering for 2-hexadecyl maltosite. So the first one shows to you the sample in dry condition. So this spacing is 3.1. And then for the hydrated here, you can see the same lattice spacing, okay? And this spacing 4.3. So as you compare between dry and hydrated, so you can have higher value for hydrated, means that the molecules swell further, and then there is interaction between molecule with water through the hydrogen bonding. So this repeat distance between the peak shows to you the formation of lamellar phase for 2-hexadecyl maltosite. Okay, now let's move to the second part, phase behavior of the branching glycolipid water system towards the formation of hexosome and vesicles. So here, these are the techniques that have been implemented in the measurement. So first one is the critical aggregation concentration by tensiometer. Secondly is the formation of hexosome from 2-hexadecyl glucoside. We measure the formation of hexosome by using particle sizer to determine the size, and transmission electron microscope to see the morphological properties. And then the formation of vesicles from 2-hexadecyl maltosite also by using particle sizer and TEM. And then finally, we investigated the effect of aiding cosurfactant to the system. So we measure with the particle sizer and TEM. So these are the results. So 2-hexadecyl hexosome producing by 2-hexadecyl glucoside, and then these results from the CAC, critical aggregation concentration. As you can see that the the twin AT lower down reduce the CAC value of 2-hexadecyl glucoside, means that it enhanced the stability of 2-hexadecyl glucoside hexosome formation. So this one is the particle size of 2-hexadecyl glucoside alone. So the size is 144 with the polydispersity index 0.251. So this one shows to you the micrograph image by TEM that visualized as hexagonal or close to spherical shape of hexosome. However, this sample are not stable and start to precipitate after 5 days onwards. So that's why we introduced and investigated by using different twin series of also non-ionic surfactant. So this proved that the longer chain length of twin series, okay, twin AT, enhance the stability of the hexosome by reducing the particle size and lowering the polydispersity index. So this is a mixture of 2-hexadecyl glucoside and twin AT. So then this is the illustration on the formation of vesicles from 2-hexadecyl maltosite. So it formed self-closed lipid bilayer known as vesicles. So this one is the results from critical aggregation concentration for 2-hexadecyl maltosite by tensiometer. So you can see the CAC break point when you add the anionic surfactant to the system. So when you measure the particle size and also the morphological properties by using TEM, you can see that if the sample of 2-hexadecyl maltosite alone, it produced multilamellar vesicles with greater size, less than 200 nanometer. When you add anionic surfactant of AOT and SDS, you can form a better particles or vesicles with unilamellar vesicles with high polydispersity. So now let's look at the third part, influence of branching glycolipid on a modern nanoemulsion as drug carrier system. So in the beginning, we formulate nanoemulsion by low energy emulsification method by using phase inversion composition. Means that changing the ratios or composition of the spectrants, water and oil, but maintaining the temperature at 25 degrees Celsius. So this can be done by wise addition of water to the sample. So then by this technique, you can form nano droplets of emulsion known as nanoemulsion. So these are the investigation that have been done. Okay, the observation of the sample and the size by using particle sizer. And then we also investigated the stability by using particle sizer and to-be-scan stability analyzer. And then we characterize the nanoemulsion morphological properties or image by using cryo-TEM. Then finally, we have conducted the drug delivery study, in vitro release of drug. So these are the stability study of nanoemulsion that observe that determined by the zeta sizer nano ZS by using dynamic light scattering techniques. So for the first figure here, okay, the Cremo4EL nanoemulsion only, the model drug, the model nanoemulsion system was slightly influenced by storage temperature. You can see increasing in droplet radius could observe for all samples at different stored at different temperatures. Whereas at the second one is the mixture of Cremo4EL with 2-hexadisylglucoside nanoemulsion, which is possess the smallest droplet radius compared to Cremo4EL nanoemulsion or Cremo4EL mixed with 2-hexadisylmaltoside nanoemulsion. So the size of nanoemulsion stored at 25 degrees Celsius was not changed up to 4 weeks, the most stable system. And then the size of nanoemulsion stored at 37 should rapidly increase in size. So this shows destabilization process. And then finally, the third one is Cremo4EL mixed with 2-hexadisylmaltoside nanoemulsion showed only a slight influence of storage temperature on droplet size. However, it is more stable compared to the model nanoemulsion of Cremo4EL only. Okay, so this is the outcome by the stability analyzer. As you can see here, this graph is the highest graph, shows to you the smallest the droplet size, the more droplets are in the sample, okay, hence the higher the backscattering intensity, because this measurement use the light backscattering techniques. So this proves that the nanoemulsion of mix between Cremo4EL with 2-hexadisylglucoside is the most stable system. And then this is a nano droplet size and morphology image by cryo transmission electron microscope. So you can see in the middle is the water Cremo4EL mixed with 2-hexadisylglucoside with medium chain triglyceride oil, which produce the smallest droplet size, and then you can see monodispersed there. So this proves that this glycolipid can enhance the stability with smaller droplet size of the model nanoemulsion system. And then finally, we have conducted the drug delivery study. So by using membrane dialysis bag for 24 hours, okay, so this is the outcome, which proves that the 3 nanoemulsion can release the ketoprofen very rapidly, very fast in less than 24 hours. So this is desirable because when we feel pain, we want to release the pain immediately. Compared, you take a tablet, a solid, okay, it have a slower rate compared to when you take in the nanoemulsion solution, okay. So this we compare also with the reference oil solution, which is lower the release of drug from the system. Okay, so with this, I can conclude that the natural light branching glycolipid of 2-hexadecylglucoside and maltoside exhibit rich phase behavior and versatile nanostructures in which 2-hexadecylglucoside form hexosome in aqueous media and further enhance the stability with the presence of co-surfactant twin 80, whereas 2-hexadecymaltoside can form vesicles and further enhance with the presence of anionic surfactant with unilamellar vesicles. And then finally, nanoemulsion possess a smallest droplet size when the reference system camera 4EL mixed with the 2-hexadecyl glucoside with the highest stability. So these findings justify that branching glycolipid provided an alternative non-ionic surfactant with interesting phase behavior and high potential nanoparticles, which could be used as new drug carrier system in the future. So this is my groups, my PhD students and master students that are also currently investigated on psoriasis disease, diabetic, and so on. So these are the instruments that are available in our center. Maybe we can collaborate in the future if you want to use certain equipment in our center. So with this, thank you.